Thank you for joining us for part three of our IEC support videos. So if you haven't seen the first two, feel free to go back to our webinar page where the past videos will be and you can look back on those. The presentation itself is roughly about 15 minutes, and if you have any questions, you can just put them into your question panel and we'll get to them at the end.
Welcome to today's tutorial. Let's get started. Today we are going to be looking at IEC 61131 subroutines. We'll be looking at examples of using subroutines accompanied with video demonstrations. As always, we'll be finishing with a Q&A session. In the Cscape Project Navigator, there is support for three types of logic modules. These are main loop modules, subroutine modules, and user-defined function block or UDFB modules. Modules in the main loop modules group are executed on every scan of the OCS logic. Our examples up to this point in the previous videos on this topic have all used main loop modules. Subroutine modules are executed by being called from the other modules. Data may be passed into the subroutines as input parameters and passed back from the subroutine as output parameters. Private variables are also available but are not instantiated. Our examples will demonstrate the implications of this fact. UDFB modules are also executed from the other modules. Again, data may be passed into the UDFB as input parameters and passed back from the UDFB as output parameters. Private variables are also available. For UDFBs, input, output, and private variables are all instantiated. We'll be looking at using UDFBs in a future webinar, so make sure you keep an eye out for that. First, we're going to be looking at IEC 61131 subroutines. These subroutines are a way of creating code which may be executed at multiple points in the logic but only needs to be written once. We're going to create an example where the current level of liquid within a tank will be used to calculate the volume of liquid in the tank. For this, we're going to assume a flat bottom tank for our example. In structured text language, or ST, which is typically considered the language best suited to implement this type of calculation, the code is very simple. To get our liquid volume, we take our value for pi and multiply it by the square of our tank radius, and then by the level of liquid in the tank. Obviously, with one tank, we would just add this code to one of our main loop modules. But what if we had 4 such tanks in our plant, or even 44? Good programming practice tells us that we should just keep one copy of any logic in our application. Why? Well, following the concept of DRY programming, or don't repeat yourself, basically having just one piece of code for a specific functionality makes the code much more maintainable. This is where the use of subroutines is a key feature. For example, if we decide that 3.1415 is not an accurate enough representation of pi in our application, we might want to change it and take the first 7 decimal places of pi. If the code is encapsulated in a subroutine, we have one change to make. If not, the number of changes we need to make is the number of tanks we have in the system. As you can imagine, if we have many tanks in the system, this could be a very time-consuming process. This is the subroutine we will be using to calculate our volume of the liquid in a tank implemented in structured text. There will be a demonstration on this in a moment, but first some points to note. When adding a variable to the tank volume calc variable group, we are asked to specify whether the variable is an input, an output, or private to the subroutine. Input and output variables will be displayed as such when calling the subroutine within the program logic. For example, here the subroutine will appear as follows in a function block diagram. We can see which of the types is applied to each variable in the attribute column in the project navigator. After adding the subroutine block, we see it added to the project group in the project toolbox, from where it can be dragged and dropped into the various modules that make up our application. Here's a quick snapshot of what we will be looking at in our video demonstration. Here's the main loop module where we will call the subroutine. In this case, we've implemented 3 tanks, all within an FBD main loop module. The variables for the radius, the liquid height, and the liquid volume are all created as arrays. In a later tutorial, we'll look at using a structure to store all the data for a single tank as a composite data storage item. Now it's time for our first video demonstration. So let's take the subroutine we just created and put some logic around it to illustrate its use. I'll start by creating a new main loop module. I'll create a new logic block and we're going to work in FBD. Now I will name this tanks. As discussed on the last slide, the added tank volume calc subroutine we created will appear in the project folder in the project toolbox. So we can go in there and we're going to drag and drop 3 copies of the subroutine into the logic to handle each of the 3 tanks. Now I'm going to make these blocks a little wider so that we can see all the variable names associated with the subroutine for the inputs and the outputs. Now let's add some variables to put our subroutine to use. In our tanks module, I'm then going to add some variables. First, I'll start with the radius. I'm going to name this variable fTankRadius. The f prefix here is to indicate that the variable is a floating point or real variable. So let's change the type of that variable to real. Finally, I'm going to give the variable a dim setting of 3. This creates an array that allows us to store the radius of the 3 different tanks, where the indexes 0, 1 and 2 in our array correspond to tanks 1, 2 and 3. Similarly, we'll add a variable for the liquid height. I'm going to call this fTankLiquidHeight. Again, this is a real value with a dim of 3 for each of the 3 tanks. And from those 2 values, we're going to produce our output, which is a third floating point value, which I'm going to call fTankLiquidVolume. Again, I will give this a dim setting of 3. With the subroutines added, we'll now add the input and output variables for each of the subroutine blocks, which I will do off screen. I will select tank radius 0 for the first tank, then tank radius 1 for the second tank, and tank radius 2 for the third. Note, when expanding out the variable names in the select variable box, only the first and last variable is available for selection. This limitation was introduced to improve the response time of Cscape when building the variable list. So, if you want other than the first or last element in the array, just select either the first or last item and manually change the index. Now I will select my tank liquid height variable, and again I am selecting index 0, 1 and 2 corresponding to tanks 1, 2 and 3. Then I will select my output, which is my tank liquid volume, and again I will select the index corresponding to each tank. Now, once I have all the variables in place, I can make the required connections between the variables and the subroutines, which I will do quickly now. In this second part of our demonstration, we're going to look at how we can use graphics with our IEC subroutine. Okay, now we've created the logic to maintain these 3 tanks. We're going to add some graphics to show off the functionality on the XL4 screen. So let's open the graphics editor. The first thing I'm going to do is create a slider which we can use to change the level of liquid in the tank. Obviously, in real-life applications, the value will likely come from an analog input, either directly or derived in some way. But for our demonstration, this will work fine. A current limitation of the Cscape slider is that it can only be driven as an integer value. I'm going to have to create an intermediate data value to store the integer for the slider, which is then used to set the floating point version of the data point. Coming back out of the graphics, we'll add a new variable, nTankLiquidHeight, again with a dim of 3, but this time it will be an int type as indicated by the prefix n. I'm going to add the first integer level variable for tank 1 ready to be copied into the real representation of the tank liquid height. If I just connect that across though, you will see that the connection displays in red, indicating that something is wrong. The problem is that IEC is very strict about not allowing variable types to be mixed. So, if the input to a function block is an integer, for example, it must come from an integer variable. In this case, we're trying to take an integer variable and write it straight to the real variable, which is not allowed. So let's make a bit of space here by moving the logic to the right and then go into the conversions group in the project toolbox. We're going to drag on the convert to real block and drop it into the logic. Let's extend the width of the block slightly to see the actual text of the block, any to real. That will allow us to create a slider, as we now have our integer value that will be accepted by our slider, which is copied from the original variable, which is a real type value. That will then be used to call the subroutine to execute the rest of the logic. That tells us that the block will take any data type as an input and will produce a real output, which can be used to set a real variable or drive a real function block input. So let's use the any to real function to take the integer value and store it in the floating point store. Once that's done for tank 1, I can use copy and paste to quickly do the same for tanks 2 and 3, which I will do quickly now. After pasting these blocks, again, I will make sure I have the correct variable from our array assigned to its relevant tank. We can now go back to the graphics, and now when we access the variable to drive the slider, we can open the tree below tanks and see the n liquid height array, and then we're going to select n liquid height 0 to allow us to set the height for tank 1. Let's go to the legend and set that to tank 1 height so that we know what the slider will do. Now that is our slider completed. Also associated with tank 1, we need to add a numeric value where we can set the radius of the tank. So let's drag and drop a numeric object onto the screen. First, let's change the legend of the object to indicate that this is the radius of tank 1. Numeric objects can be driven by floating point values, but we need to set the register width to 32 bits to do this, as real values are stored as 32 bits. Then I will associate this object with the fTankRadius0 variable. We can also fix the format in which the number will be displayed on the screen. I'm going to select a 5-digit number with one of those digits being after the decimal point. We can add millimeters as the engineering units and set that user entry of the radius as enabled. Once selected, we can tell the object that the display format for the numeric is real/floating point. We can also set a limit for our radius, which I'm going to set between 0 and 5000 millimeters. When we set our format to real/floating point, our display format got reset, so let's change that back to a 5-digit number with one of those digits being after the decimal point. We can now copy and paste this object to show the volume of liquid within the tank. We'll go to the object properties and select the appropriate variable, which here is the fTankLiquidVolume0 variable. Then turn off the enable for editing, because the volume is calculated by the subroutine from the other values. And finally, change the legend appropriately to show that this is the volume. Now, going back to the screen, note the difference in the button style between the editable and non-editable numeric data items. We are now ready to download that to the OCS and try changing the values of the radius and liquid height and see how the liquid volume changes accordingly. Here, I replicated the graphics I just created for tank 1 for tanks 2 and 3 and put them on one screen. If I use the sliders to change the liquid height in the different tanks, you can see the liquid volume for the respective tank changes according to the calculation from my subroutine. Thank you for joining us for today's tutorial. The Q&A session will begin shortly.
Okay, short and sweet this morning. Not seeing any questions just yet, so I shall take you back to the screen. So as I said, this was part 3 of IEC support. So if you haven't seen the previous 2 parts, feel free to go back and watch them. There will be a fourth part coming. We'll be confirming a date closer to the time, but there will be a part 4 to that series of IEC videos. Next week we do have high-speed outputs, and then into trends and data parsing. Yeah, all past videos are there if it's a different topic, and if there's any topics we haven't covered and you'd like to see covered, feel free to drop us an email and we'll see if we can get one in for you. On that note, I think that is it for this morning. Thank you all for joining us, and we hope to see you again next week.